So the topic of today, as I mentioned, is non-destructive testing and monitoring techniques for additive manufactured metallic parts. And I'm very happy to introduce our two speakers of the day. So we have first Steve MAHAUT, who is a senior expert at CEA. Steve has been involved in non-destructive evaluation for more than 30 years, starting from a PhD in physical acoustics in the field of ultrasonic phased arrays techniques. He then broadened his expertise to wider fields of research and other NDE techniques. He has been in charge of R&D projects for various industrial sectors, such as energy, oil and gas, and transports. And prior to head different laboratories within the NDE department at CEA. Steve is in charge since January 2023 of the monitoring, control, and diagnostic section, which gathers 4 laboratories and about 100 of staff involved in advanced instrumentation methods related to NDE and monitoring. And next to Steve, we are happy to welcome Anaïs BAUMARD, who is a research engineer at CEA. Anaïs' research focused on the understanding of metallic additive manufacturing processes from an experimental and a numerical point of view. Anaïs conceived and implemented the first numerical model at CEA dedicated to the prediction of metallurgical grain structure formation of components manufactured using the selective laser melting process. Today, Anaïs is the operational supervisor and lead research engineer of the PRISMA platform at the Technology Research Division of CEA, and which is a multi-process robotic platform dedicated to metallic additive manufacturing. So I will now leave the floor to Steve and Anaïs for their presentations. I invite you to leave your questions in the chat, and we will take them after the presentations. Thank you.
Okay, thank you, Lucy, for your introduction. Okay. I'll give my presentation, and then Anaïs will follow on the Prisma platform. Just let me know if everything's okay for the presentation, I hope. Okay. Okay, so do you see the presentation in full screen?
It's not in a full screen at the moment, Steve.
Okay, I'm just getting back. Is it okay now?
Not yet.
Okay, I will change I will change the settings then.
Problem.
I don't know what's going on. Just 1 minute. Ouais, mais ça n'a pas fonctionné. Je vais essayer comme ça.
So now it's working.
Okay, thank you.
Thank you.
Okay, so sorry for this delay. So I'm going to talk about non-destructive testing and also monitoring activities that we have carried out at CEA within the frame of the Grade 2XL project, but also we'll present some activities related to other European and national projects which are dealing with the same kind of activities and the same kind of problematics. Just 2 slides concerning CEA and our department. So CEA is quite old. let's say, RTO founded in 1945, which is divided into 4 main units and devoted to different national missions at CEA in France. So we deal with defense and security, with specific application, digital transition, and this is the department that we are involved in. We are also leading some activities related to energy transition, both for nuclear and also renewable energies. And we have some activities for climate, astrophysics, nuclear particles, and so on, within the fundamental research unit. So CEA gathers about 21,000 of the whole people staff, including more than 1,500 PhDs. And we are spread within France as part of civil defense centers. And also we have some regional platforms for technological transfer. And we are very active in the field of the digital transition and technological research. So these are a few key numbers that I'd like to focus on. So we are the first European RTO patent deposit. We have about 240 startups that were created from CEA, and a lot of industrial partnerships for all kinds of activities. Now, if I'm going to my department, and the department which is involved in Grade to Excel project, it is about 300 people, 230 permanent people staff. We develop probes, methods, and sensors for 2 main activities: chemical and radiological hazards, including nuclear activities, and non-destructive testing and monitoring. And of course, I will mostly speak about this activity in my talk. So when we are dealing with non-destructive testing, we are considering these methods: ultrasonics, currents, and electromagnetic tomography, some activities related to infrared thermography, active infrared thermography, and also some activities related to reflectometry, electrical reflectometry, and optical fibers for monitoring, and also for passive methods. The department is divided into 3 main sections: ionizing radiation, instrumentation, and metrology, which I will not talk about, monitoring, control, and diagnostic section. So I am the head of this section. And artificial intelligence and simulation section, which gathers all competencies and skills related to simulation of NDE, and also some activities related to artificial intelligence, machine learning. So this can be artificial intelligence driven by data or driven by models, let's say connectionist AI or symbolic AI. So as Lucy has already talked about Grade to Excel project, I will not get back to this, except that the main contribution from CEA within this project are completely dedicated to evaluation of non-destructive evaluation techniques for build parts in terms of defectology and composition. So these are activities carried out and related to the various that were shown by Lucy. And the other main activity is related to the evaluation of monitoring techniques during the manufacturing of these pieces. So if we focus on these various activities, I will just recall some key aspects of additive manufacturing related to NDE. First, of course, there are the diverse additive manufacturing processes, and they have different maturity levels. Here we focus on metallic parts. So if we have been working with a specimen or process such as powder bed fusion, direct energy deposition, WAAM, wire arc additive manufacturing, but also wire laser additive manufacturing, metal better jetting for different applications. There are no straightforward links between materials and processes, and from an NDE point of view, and that's a critical point, it's very difficult to have some acceptance criteria. So the defect criticity is not established for all industrial sectors. But of course, there are a lot of ongoing works related to standardization, both at ISO and ASTM, for instance, related to this application. So there are finally different maturity levels, either for NDE and for standardization of these processes. Now, if we look at the additive manufacturing parts, there are specific issues related to NDE. First, usually these parts are quite complex because it's the natural way to solve the complexity is to build those kind of complex structure using additive manufacturing. For consider lattice curves, 3D internal canals, etc. Of course, this can be done with parts, but it is done at one step. And there can be rough state of surface, especially for one application, due to the thermal history of the process. There can also exhibit some strong residual stresses, and there can be various anomalies such as excessive distortion, deformation of the parts, cracks, pores, lack of fusion, keyhole defects, etc. So at CEA, we work at different stages. Before manufacturing, we can try to predict some part characteristics, and we can try to evaluate parts assessment. So using simulation, we can, for instance, try to optimize an NDE setup. During manufacturing, then we can evaluate online monitoring techniques to evaluate the repeatability of the process. The key issue would be to be able to make some feedback to the machine during the fabrication. And for instance, if we detect a defect, then we can solve the defect at the next manufacturing stage or at the next layer or welding layer. And after manufacturing, of course, we are investigating post-manufacturing NDE solution to get the expertise of the parts and mockups. So if I come from simulation, we are mostly working and developing the CEA software dedicated to non-destructive evaluation using the same techniques that I have already quoted, ultrasonics, electromagnetics, radiograph, and computed tomography, thermography. And we have various approaches, various codes that can be semi-analytical or fully numerical techniques in order to get calculation times compatible with the application that is desired. So if I start, for instance, with an application that has been made about WAAM application, we have worked with another department at CEA from the nuclear and renewable energies about the possibility to couple the process additive manufacturing process simulation codes and NDE simulation codes. And for this, the main idea is to be able to assess the controllability of a WAAM part from the knowledge of the welding and process parameters. So at the left part, you can see some activities that are leaded in another department of CEA, direction of energy. So there are some tools in order to predict the shape and the microstructure of the WAAM components. And the idea was to be able to transfer this kind of geometry and structure to the NDE simulation codes that we develop SIVA in order to evaluate the effect of the raw state of surface towards the inspectability of the component. So you can see on this slide, we have one part that has been built. And at the left hand side, you have the simulation of an ultrasonic beam, which is propagating into this kind of parts. So obviously, there are some distortion of the beam. And we can see the comparison at the right side of this slide with a smooth surface. And of course, the beam is stronger, less attenuated, and it has a homogeneous shape. So what has been done in this project with the knowledge of experts from the direction of energies, we have made a simple, let's say, phenomenological description of WAAM state of surface. So starting from the description of mid-height, speed, weight, and so on, number of passes, and the center distance ratio between two weld beds, then we are able to predict, let's say, canonical shape, which would be representative of the final state of surface. And then we have built various parts with various parameters. And finally, we have made some experimental and some simulation related to these parts in order to check the comparison between experimental and simulation results in order to predict the beam which would be transmitted through this kind of surfaces. So if you see this comparison, the main point is not to be completely accurate with respect to the position of the echoes. The main point is to be able to have a correct noise level, both from simulation and experimental, in order to have some statistics ideas of what we can observe in one part using various WAAM parameters. So that's a project that we have carried out with this project. Now, if we move to online monitoring, so then we are focusing on monitoring aspects related to building a part. I need to talk about a quite old project which has been carried out 8 years ago. It was a national funded project called I Am Sure, with various partners in the industrial and also BIM, which was a company dealing with direct energy deposit. So it's not WAAM, but it's also an additive manufacturing process. We have developed some contactless non-destructive evaluation techniques, which are based on laser UT method. So the idea is to generate, using a laser source, an impact laser on the surface of the part, and using an interferometer, also a laser interferometer, we can check, when we can measure waves that are propagating inside the part and which are finally getting back to the interferometers. And we have been using two different ways to manage this kind of application. We can radiate rather surface acoustic wave at the surface of the component, and we can also generate resonance mode, which could, for instance, be used to evaluate thickness of the specimen during its fabrication. So this is what it looks like. We have made with BIM and partners some walls in order to check the influence, the impact of various parameters. We have made some pristine walls with nominal parameters, and also we have evaluated the impact of various parameters which have been declined. So for instance, we have reduced the power, increased the hatch, and we have made some various walls using various parameters. So this is the cartography which was caught during the fabrication of the pristine walls. And you can see that if you look at the lookup table at the right side, this is quite homogeneous. So we display here the maximum amplitude of the relay wave. So we can consider that if we are using pristine parameters in order to get a pristine mockup, we have quite a homogeneous results. If we modify, if we reduce the parameter, so that there will be some distortion, then that can be measured using our. I can also just show you how it looks like within the machine. So this has been made inside. This has been made inside a DED machine. It was a BIM machine. You can see here the real-time measurement using the laser ultrasonic system. And this is what it looks like. So you can see here the wall that has been built, and you can see the laser ultrasonic system which was used for the application. If I'm just moving a few seconds later, okay, then we build again some additional layer of the wall, and we will reduce the measurement. So that's okay, but this was made for, let's say, fabrication of wall and then stop and come again. Oops. We have made this also with resonance mode application. So here we measure in real time the thickness of the component. So this signal corresponds to dynamic measurement of the thickness during the fabrication of the part. And here again, at the left, at the right-hand side, you can see the thickness that can be measured during the fabrication. And another with various parameters. And finally, we have also made a complete synchronization between the fabrication of the part and the measurement of the part using an optimized system. So you can see now in this video that the part is built, and in the same time, the laser ultrasonic system, the thickness of the part, and we can also detect some, let's say, large defects during the fabrication. Okay, now if I get back to Grade 2 Excel application, we have been also investigating some laser ultrasonic detection, but only in a passive way. The idea here was to use the laser system only using one interferometer in order to check if the process is going smoothly and if there are no defects during the process. So it's kind of events detection method. And for this, what we have made is we have only used the vibrometer. So this has been made with Technical University of Delft. And you can see the measure, the continuous measurement of waves, ultrasonic and acoustic waves during the fabrication of the parts. And we can see here the signal is increasing during the fabrication of a bed. And there is a very strong amplitude here, which corresponds to the apparition of flows inside the welding. So this is a time signal, and this is a time frequency representation of it. And it is showing that we are able to correctly detect some distortion. Okay, the same application within Grade 2 Excel has also been targeted onto the elemental composition evaluation using X-ray fluorescence. And for this, we have used detector and X-ray tube in order to be able to evaluate the proportion of elements, of chemical elements during the fabrication of the part. So here, this is just a test that has been made in lab condition, but you can see the welding, and you can see a setup which includes X-ray tubes, a detector, which allows to measure the spectrum of X-ray backscattered to the detector. And using this, we are able to evaluate the elemental composition of component, which was made of two components from stainless steel to Inconel alloy, using a continuous variation of those two wires. And what is important here is that we can quite correctly measure the variation of the nickel element, which allows to evaluate the proportion of Inconel and stainless steel within this fabrication. And the last part of this presentation deals with non-destructive testing methods after manufacturing. So the reference method that we use at CEA is the X-ray tomographic method, because it's considered as the reference ND method for complex parts, especially when ultrasonics or other techniques cannot be completed because of the shape of the specimen or the raw state of surface. And for this, we have been dealing with specific tomography and analysis method, both for dimensional analysis or porosity analysis. And we have some tools in order to evaluate the capacity of these methods with comparison to not so mature method for complex parts. We have also investigated on large parts. So this was made with two partners from Grade 2 Excel project before the Grade 2 Excel project was started. We have evaluated the possibility to inspect a blade of a marine propeller made by WAAM. So you can see on this slide the inspection using a phased array, which is moved over the 3D shape of the blade. And this is a specific flexible phased array, which is able to conform to match the specimen geometry. And you can see on the right-hand side the result of this inspection, and you can see some in cross-section view, given some flows which are inside the specimen. This was about 1 millimeter pore. Also work other partners within the Grade 2 Excel project in the same kind of activities in order to evaluate and to validate some process parameters related to the fabrication of various parts. So here with Naval Group and Delft, again, we have evaluated the composition and the results for various coupons specifically made for the project. So these coupons were obtained with various parameters, machine parameters, and we have compared some ultrasonic inspections and destructive tests on the same samples in order to correlate the defect size which were obtained by destructive tests versus the ultrasonic amplitude. And of course, the goal is to be able to assess defect sizing from NDE in order to know the size and the number of defects within the components. Okay, so I will skip this part because it's more related to homogeneous properties. Finally, in other projects, we have also evaluated the possibility to correlate some data coming from all the manufacturing process, meaning from the shape, design data, the strategy of integration, layer data, and so on, the data obtained during manufacturing, and finally the data from the NDE test, and try to be able to correlate all this data to understand the phenomena. And so this was made during the INCHE, which was another European project. And this is just one example on the WAAM application, for Arc Additive Manufacturing application. We have made some tomography of a part, which was built, and we have registered all the data, the machine parameters data during the fabrication, in order to see if there are some correlation between variation of the process parameters during the fabrication and defects observed after the fabrication. So this is what we have. We have some data registration tool to synchronize spatially and timely the data from the machine parameters. We have the tomography. And finally, we can relate one given pore, for instance, to some variation observed during the fabrication. So as a conclusion, and I'm sorry for having been too long, we have worked about design of NDE method, monitoring and expertise build part, and all of these works have been carried out within a national or European project or some industrial project. And our next step now is to evaluate this strategy with the Prisma platform, which Anaïs is going to present. So I thank all my colleagues, and especially Audrey Gardao, for all these works carried out in to Excel and other projects. Thanks. I think that Anaïs is going to.
Thank you, Steve. There are maybe questions. Can you hear me?
Yes.
Yes, Steve, there are a couple of questions for you. Maybe we can take them now. Yes. While Anaïs is setting the slides. Okay. So the first question from Rick Jacob: how can CEA users obtain the WAAM plugin?
I'm sorry. How can CEA?
Okay. How can the CEA users obtain the WAAM plugin within the?
Ah, okay. Okay. Yeah, it's developed with CEA, but it's not available in the commercial software. I think that this is a plugin that has been evaluated that's a question I can get, and if Rich, hello Rich, is interested in this plugin, I think I can check how he could get it. We have to check this.
Okay, thank you. We will pass on your contact details with a replay, so participants can also reach out to you.
I have seen a question from Christopher Thompson. Yes, about the positioning of the UT probe over the blade propeller. Indeed, we have first made a 3D CAD description of this propeller using optical scanning system, and then we have used this 3D CAD description within CEA in order to guide the robotic inspection. So finally, we measure first big propeller.
Thank you. And there is one more question from Tarun. Would the defect sizing be applicable to all types of WAAM processes or be particular to the specific welding subsystems?
It's it's a difficult question. I would say that of the defect that we have detected were quite small, but we have machined most of the parts that we needed to carefully investigate, especially during the grade 2XL project, because we wanted to be sure as most as possible as the defect size. And for this, we have machined the pieces in order to be flat or to be smooth. The idea of the simulation, and we have also made some other application with no grinding, with no machining on the surface of the parts, in order to see the impact of the state of surface toward the size of the defect that we can deal with. So let's say that if we have raw state of surface, we can, let's say, depending on the application, go to millimeter size defect, and we can go below if we have some flat surfaces. But for any kind of application, it has to be evaluated, it has to be measured. It's difficult to have a very generic answer about this.
Thank you. And there is one other question from Christopher Thompson. How are the layers in WAAM modeled in SIVA?
Yeah, here again, it was based with direction of energy at CEA. And the idea we had phenomenological solution. So we were considering weld beds as elliptical shapes, and considering the weld beds height and width and the center of distance, we were running some statistical calculation of possible state of surface. So that was a quite geometrical problem. It was not a complete welding process simulation, unless, well, although this kind of simulation process is also made at CEA within this department.
Thank you, Steve. I think we can now go ahead with Anaïs' presentation.
Okay, I will stop and let Anaïs take this.
Thank you very much, Steve.
Okay, so hello. Ah oui, il faut que tu coupes le son, je pense. Bon, oui, et je vais mettre le son plus fort ici pour que Okay, so is everyone able to see my screen?
Yes, we can, but not in presenters mode.
Yes, we can, but not in presenters mode. Okay.
Yeah, that's good now.
Okay, perfect. Okay, perfect. So hello to everyone. Now I will be introducing to you the Prisma platform that aims at developing the digital continuity for direct energy deposition process. So here the presentation that I will show you today has been prepared with Clarisse Poitvin, who is currently the Deputy Manager at CEA List on the concern about innovation and platform. So first of all, some elements about the Prisma platform itself. Here you can see if the slides are moving. Okay, you're still on the first one, right?
Yes.
Yeah, I think it's maybe too slow. Peut-être. Okay, we'll try to wait. We'll try to do it differently. Steve will be sharing the presentation because obviously his connection is way better than mine. Et c'est pareil, il faut que tu fasses tout l'écran. Tout en haut, tout en haut. T'as cliqué à côté. Arrêtez le partage. Envoie ta... Ouais. Et du coup, celui que tu veux. Okay, so second try. Oui.
Now it's good.
Okay, perfect. Okay, so second try. Merci. Okay, perfect. So here you can see the platform. You can see a picture of the platform. Et... Ouais, si c'est bon, vas-y. Juste que tu fasses. Parfait. Okay, so here you can see a picture of the platform, which is a multi-process robotic platform, as you can see. On the left, you have the manufacturing robot, which is a COMAO N220, connected to the welding generator in order to manufacture the parts and to deposit the metallic components on the two-axis support located at the center of the picture. On the right, we have a second robot, the KUKA KR360, that is equipped with a machining spindle in order to achieve the manufactured part. So the two-axis robot plus the two-axis support on the center, because the support can tilt around the horizontal axis and also turn around itself, plus the machining spindle and a precise linear axis located at the extremity of the COMA robot, offers a 16 axis multifunction platform. So to give you an idea of the size of the platform, here is a representation of the deposition capacity of the platform. So it's 2 metered height and 2 metered width, and it can welcome parts that weight up to 3 tons. So if you have still some trouble visualizing how big is the platform, here is a picture, if it's charging. Here is a picture of the colleagues. Okay, can you see are the slide changing, or you're still on the third one?
We are still on the third slide.
Okay. Wait, differently. Là, il a bugué de... Okay. So... Non, c'est pas du tout. Ouais. On va y arriver. Surtout qu'elle est plus légère que la tienne. Est-ce qu'elle est sur la clé? Non. Okay, I'm sorry for that. Non, ça bug toujours. Ouais.
Do you want me to try and share your slides, Anaïs? You can...
Maybe I can try that.
Quickly send them to me.
Which is very weird, because the presentation is way lighter than Steve's one. So I don't really understand. Je vais faire un transfert à Lucie. Vas-y, c'est une dernière fois, mais...
Do you see the screen for slide number 4?
We can see the slide, but with like the notes, you know.
Hmm. Okay, Lucy, I'm sending you ASAP the presentation. Et là, c'était pas sur la clé, hein. On est d'accord.
Which slide can you see now?
Now we can see the slide number 4, but with the, you know, the notes, and the next slide is also visible.
Il est planté.
Bon.
Ok. Et vas-y, essaie de quitter le panorama, ça fonctionne même pas. Ah si, là ça a fonctionné.
Now we see
Troisième
the...
tentative.
Okay, okay, we are trying one more time.
Et on
Last time, let's say.
met-
You see slide number 5?
Yeah, but again with the notes. And yeah.
Okay, Lucy, I just sent it to you. I'm sorry for that. And there is no videos or very big, heavy elements, so...
Oh, mais là, il est en plein écran.
Ah oui, je sais bien.
Sorry for the participants. We will be a little bit delayed, but I'm opening now the slides. Let's try.
Yeah, on a essayé. Okay.
This is not that one. Can you see the...
Yes, yes, we can.
We were here?
Okay. Yeah, perfect. Okay, thank you very much, Lucy. So I'll ask you to change the slide. I'm sorry.
Yeah, sure.
Okay. So I was saying that if you have some difficulty visualizing the size of the cell, here is a picture with some of the colleagues you may know, especially Audrey that you can see on the right, that are standing up to nearby the support. And so you can see that the upper part of the support reaches their neck or shoulders. So it's kind of big. Next slide, please, Lucy. Okay, so here are the experimental equipments of that are composing Prisma. So you have here currently 2 technologies that enable to manufacture part with the wire arc additive manufacturing process. So the CMT Fronius generator on the left, and also a GIS one that enables some manufacturing more like a MIG-MAG process. There is also, as I told you before, the robots that enable the machining of the parts. So it's a multi-process platform on this in this sense, because we can manufacture but also machine. And something that I didn't talk about yet, but which is directly linked to what Steve just presented, is that the platform is not only focusing on the deployment of the digital continuity of the manufacturing, it also focuses on developing in-process monitoring and non-destructive testing. So I won't go into detail because Steve gave a lot of information about in-process monitoring, different base monitoring, acoustic, optical, electrical, but the platform really aims at helping the mastering of the process doing some monitoring. So this was regarding the experimental aspects and the experimental elements of the platform. Here are some more information about the digital continuity of the manufacturing. So the platform has a continuous digital environment that is composed of several modules. Here you have some illustration. I will list them quickly to try to catch up a bit with the delay. So first, there is a digital twin of the platform. Also, all the robotic programming software that enable the generation of the trajectory for the robots. We also have numerical models of the physical process of metallic deposition. Here on the bottom left, you have an illustration, also with the custom device. So it's the colleague from the direction of energies that Steve was talking about, that used and developed this model. We also have physics-based numerical model of the monitoring and the control with CEA. Steve also detailed that aspect quite precisely, so I won't go into details. And a lot of efforts are also made on working on the development of a database for the collection and organization of the data that are generating during the manufacturing, by the process itself, by the instruments that monitor the process. And a lot of colleagues also work on the development of AI methods for the processing of the data. You can change this. Okay, thank you. So here is the organization of Prisma. So as I detailed before, there are some experimental equipment, some digital environment, how everything is organized together. So in yellow, you have the physical infrastructure that enable the manufacturing of the parts, in-process monitoring, and robotic non-destructive testing on the built part. You also have, as I said, all the modules that enable the storage of the data that is generated, its post-processing, and that gathered the methods existing for the processing of the data. In red, here you also have the digital environment that gathers all the modules, the numerical modules, so the digital twin, the multiphysics model, and also something that I did not notice before, but some tools that helps the estimation of the carbon footprint of the manufacturing itself. All the three blocks are interconnected and interact with each other, guaranteeing the digital continuity of the manufacturing. So that was for the description of the element composing the platform. Now I will talk about some topic of interest and the main theme of research and developments we're working on currently. So as you imagine, due to the fact that the main aim of the platform is to offer digital continuity of the manufacturing, we are currently developing some digital solutions. I heard modules that are interconnected between each other and that are able to interact with the physical equipment. I will go very quickly on the second point because Steve presented a lot of solution on that part, but the CEA is currently working on developing innovative solutions for the monitoring of the process. So while the manufacturing of the parts is going on. The third point that is important important is the implementation of adaptive manufacturing strategies in order to correct some deviation from the fabrication, to repair a part that is currently manufactured, or to refill a built part that has been damaged. The fourth point, main topic of interest, is the use of artificial intelligence tool to capitalize the data produced during the manufacturing of the process. So that was more for research and development. Now here are some themes that are more interesting for our industrial partners, because the platform aims at deploying the technical evolutions proposed by CEA for the industrial need. First of all, because it offers the possibility to optimize the conception of the desired part, thanks to the digital twin of the platform and the different simulation models. Also, as you know, additive manufacturing, and especially WAAM, enables to do a lot of things, and so anything, and it's most of the time very hard to identify the parameters that are adapted for your specific manufacturing. So the platform also helps the development of tailor-made building strategies due to the digital environment of the platform and all the AI models and methods that help for the prediction of the behavior. Another important thing is the fact that due to the monitoring in process implemented, the data exploitation during the manufacturing of the parts, and the possibility to react in real time, it helps the detection of deviation and the occurrence of defects at every manufacturing stage. It is very important because usually parts manufactured with additive manufacturing, and especially WAAM, are kind of big. And so it is important to identify the occurrence of a defect as soon as possible in order to have the opportunity or not, depending on what we want, to interact. And finally, just before the slide after, the platform also helps our partners to guarantee the reproducibility of the process and the quality of the part. So something I wanted just to insist on is that the platform is very young, because it has been commissioned on the last semester of 2023. So here are the very first manufacturer samples that we've done at that moment. So you can see I'm not talking about parts because it's very simple geometries, single wall or multiple pass or multiple bed walls in different alloy, stainless steel, but also aluminum. And here on the right, you also have an example of machining that we did on some stainless steel wall. So now the platform is getting a bit older, so more recent work has been conducted on 316L stainless steel. It's still very simple geometries, but it's more parts than samples in the country of what I just shown before. This part was done in order to see how the platform interacts with the numerical environment, how we can collect and process the parameters, and how to monitor the process parameters. And so this is ongoing work. So I will try to finish very quickly. I just wanted to finish the presentation with some elements of context. So Prisma is a platform that is part of a bigger one that is called Prism, that gathered 5 platforms in order to offer advanced capacity for manufacturing. So here are the 5 platforms that are gathered into Prism project. So some focus on developing collaborative digital engineering, some other to implement AI methods for industry, developing digital twin for plants, and integrate some smart robotics in the factories. So all these platforms are capitalizing and adapting results from different research programs held here, conducted here at CEA, in order to help the manufacturing industry to reach their expectation. And so the fifth platform that is part of Prisma, bigger group, is Prisma, and focuses on additive manufacturing in order to the manufacturing in fabrication. And so Prism, it's like so to give you some element of context extra, the platform Prism is part of a bigger European project that is that focuses on AI and robotics, that is called AI Matters. So the project that you have here is composed of 7 nodes located all around Europe, as you can see represented on the map. And it aims at increasing the resilience and the flexibility of the European manufacturing sector through the integration of the different latest technologies that everyone has developed at their institute in order to help the manufacturing company to be the more productive. So how does it work? The project AI Matters offers to its customers some different services, like a catalog of services, in which they have support on different things linked to the 5 capacity I just evoked, so linked to additive manufacturing, smart robotics, digital twin, or AI for industry. And just to conclude with an example, this is a kind of, can you, Lucy, change to the last slide, please? Thank you. So here is an example of a service offered by the platform Prisma, linked to the AI Matters project. It's to help our partners prototyping new products with AM processes, and especially WAAM processes at the time being, using the digital tools we're having right now, and so the digital environment. So thank you very much to all of you for your attention, and sorry for the little delay. And don't hesitate if you have still sometimes any question.
Thank you very much, Anaïs. I'm actually checking out the chat to see whether there are questions. So I don't see any. So yeah, as we are a bit delayed, I will just allow me just 2 more minutes to conclude and share again a couple of slides. So thanks a lot to Anaïs, and thanks a lot to Steve for the great presentations and overview of your activities. There is one question from Tom. Can you see it, Anaïs, in the chat?
Yes. Currently, we're doing it into 2 stages. So the question, for those who cannot read the question, was the machining robot used to machine the parts in situ straight after being WAAM? Yes, currently the parts are built and the tooling is done straight after being WAAM. What we aim at doing in a second stage is to go from a step of manufacturing to a step of WAAM, and to change from manufacture stage to tooling 1, not to wait until the end of the fabrication, the manufacturing, sorry.
Thank you. So if there are no more questions, I just wanted to conclude to inform you about the next and last Great to Excel webinar that will be happening on the 21st of June on the topic of topology optimization. I actually see one more question from Utuman. Are there any open postgraduate research opportunities at CEA?
Directly linked to the platform, right? Currently not, but I think that Steve can.
Yeah. There are always some postdoc and postgraduate positions. We don't have yet one open on this topic, but if you are interested in our technique and position, stay focused. There is my mail, and you can also have a look at the opening position for postgraduate CEA website. Do not hesitate.
Thank you. So just to finish, the next webinar, 21st of June, it will be probably the last one for Grade 2 Excel. Just to announce as well, the final event of Grade 2 Excel will take place in the framework of the International Conference on Welding and Joining that will be happening in Greece in July. So if you are planning to go there, well, stay tuned, because there will be a lot of Grade 2 Excel activities as part of this event. And don't forget to follow us on LinkedIn. We also have a website where we put updates, we put the webinar replays, we put the link to the scientific papers that are produced within the project partners, and also a series of articles to disseminate the Grade 2 Excel results. So you can also reach out to me if you have any question following this webinar. I can put you in touch with the experts from the consortium. And I thank you very much for your participation. Thank you to the two speakers of the day, and we keep in touch.